Hello, and welcome back to a lecture series on molecular simulations and statistical mechanics for engineers. Today we're going to be talking about a postulate approach to thermodynamics and to understanding how thermodynamics interacts with the classical mechanics that we just learned. So it's interesting when we talk about some agglomerate of matter. In this example, let's take a glass of water, for instance. There's actually somewhere on the order of 10 to the 25 atoms in a single glass of water. From a classical mechanics point of view, from the type of physics that we've used previously, we are not going to be able to keep track of all these particles all at once with things like Newton's equation of motion or the Lagrange equations of motion. And clearly, this sort of classical mechanical technique in which we write I equations of motion for all of these particles is completely infeasible. So the question becomes, how do we study systems like a simple glass of water without ever appealing to the notions of classical mechanics? Well, from experience, we know that studying something like water is actually very simple, right? We could, if I bring you a cup of water, you could tell me what its volume is, for instance. You could say, oh, what's the volume? You could say, I can measure its temperature. You could even tell me, by looking at certain experiments, exactly when this cup of water will boil if I start to heat it up, right? So we actually do know a lot about the structure and the behavior of this matter without ever talking about classical mechanics. And the type of physics that we're using to understand these types of questions is thermodynamics. So thermodynamics is actually going to give us the tools to sort of intuitively understand these basic systems, right? Now, why can we look at things like volume and temperature versus the equations of motion when we study these systems? Well, let's think about how atoms move. So let's say I have a system, and I'm just going to draw these water molecules as circles. Let's say we have a system of water molecules. And of course, they're rotating, they're vibrating, they're moving around. And with the naked eye, even with some of the best experimental apparatuses that we have, we can't always see these vibrations that are happening, particularly at our macroscopic scale. So you and me, when we look at a glass of water, we don't see the vibrations and motions of the water molecules. All we see is a standing glass of water, right? So these sorts of types of ways that atoms can move, these vibrations, or perhaps expansions. So, you could have the particles vibrating together and not moving, or you could have the particles, for instance, all moving away from each other, diverging. So maybe your initial system was contained within this dotted little circle, and then eventually it gets bigger, right? Well, ways in which the particles move like this are referred to as normal modes. These are normal modes. Some examples: vibrations, expansions, and of course collapsing. So expanding in the other direction, inward, right? You may have molecules and atoms that reorient or rotate. You may have some sort of collective behavior or just vibrational behavior. And thermodynamics as a field is concerned with normal modes that we could observe at a macroscopic level. So at a macroscopic level, we can never see the vibrations, but we can see things like expansions or changes in volume and density, right? So really what our working definition of thermodynamics is going to be is that thermodynamics is the study of macroscopic scale normal modes. So things we could actually observe at a macroscopic scale. Before, in classical mechanics, we could have built models for things like atomic vibrations or rotations, and in molecular simulations we will. But in thermodynamics, we're going to be concerned with things that we can observe at our scale, like changes in volume, or changes in temperature, or even things like changes in pressure or density. So this is the realm of thermodynamics. What happens when we take this macroscopic view of the world? Well, we actually start to lose a lot of information. In fact, we lose track of the atomic coordinates. We lose track of atomic coordinates. So whereas before we were describing using a Hamiltonian or a Lagrangian to keep track of all these particles at once, in thermodynamics, we're actually going to lose track of these motions. In thermodynamics, we refer to this energy that can be transferred from the atomic coordinates, or we refer to energy transferred by these atomic coordinates, as heat. So heat is going to be all of the energy that's transferred within the atomic coordinates that we can't keep track of anymore in classical mechanics. Now, note that in classical mechanics, heat doesn't really exist. So in classical mechanics, there is no heat, right? Heat isn't there. Why is that? Well, the reason is that we can actually just completely characterize the energy of the system by looking at the classical mechanical work. And this is what we discussed in lecture 2. So we can look at changes in energy in a classical mechanical system, and we can say that's due to the work done by the system. I'm going to use this W prime, or work done on the system, right? So we actually, in a closed system, where we're not exchanging particles or energy, we could show with the classical mechanics that the change in energy is just directly equal to the work done on the system. And there was no invisible mode of transferring energy. There were no hidden atomic vibrations or rotations that we had to think about. But in classical thermodynamics, what we're going to have to do is actually break up this term into two separate terms. And this is essentially to accommodate for the fact that we don't know where the atoms are anymore. We can't actually calculate the work done on the system. So in classical thermodynamics, we're going to introduce a new expression for this classical W prime. We're going to say that the work done on the system can be done by mechanical work that we can observe at our scale, plus the invisible work that we can't observe, which is heat, and we denote that by Q. So this is mechanical work, and this is heat. And of course, this is the classical mechanical work. So if you could keep track of everything going on. So our new expression for the change in energy in these thermodynamic systems is going to be equal to W, the mechanical work, plus the heat. This expression is called the first law of thermodynamics. So this is the first law of thermodynamics. So you can see it's really not that interesting. I mean, it's interesting, but it's not that profound. Once we understand classical mechanics and how energy is defined and works within that framework, all we do in thermodynamics is say, we've lost track of atomic coordinates, so let's make up a new variable for what we've lost track of, right? And that gives us the first law. So it's a very simple and foundational law that we will rely on in thermodynamics. Rewriting the first law, the change in energy is equal to the mechanical work plus the heat. Now we typically, to go from this expression, what we typically do is we ignore the presence of an external field. So if we ignore external fields, this could be like gravity or something similar. So if we ignore external fields, and we say the system is not moving in space, right? So we don't have some weird reference frame problems or any sort of kinetic energy from the system hurtling through space or something like this. We're going to ignore system motion. If we make these two assumptions, which are pretty lax, we can end up by writing that this expression is equivalent to the change in internal energy. So U is the internal energy, or essentially just the energy of this system. The internal energy of the system is equal to W plus Q. Now, of course, the internal energy is then just defined as the total energy minus this external field part and minus the system motion part. But of course, they're the same exact expression. If there is no external field, there is no system motion. Now, let's think about differentially what this means. So right now we've written this as the total change in internal energy is equal to the mechanical work plus the heat. But what about a differential change? So we write a differential change as du. Now this is actually quite subtle here. So usually, you know, and if you were to write this classically, you'd have something like dE is equal to dW prime. When you write something like this, what you're saying is that the path that the energy takes, so dE is a change in energy. So you have an E1, you go by some, you change the energy by some amount dE, right? And you're at E2. But what this expression says is that the path that the energy takes doesn't matter. And if the path that the energy takes doesn't matter, also in this expression, the path that the work takes doesn't matter. Path of the work doesn't matter. So we will say that these are path independent, right? Doesn't matter. And if you remember from earlier in the class, when we studied work and we studied moving from A to B in conservative fields, we found that no matter if you take path 1 or 2, the change in energy is the exact same, right? It was independent of the path in these conservative fields. Now, ignoring an external field, we're in the conservative case, we should expect that these paths don't matter. The problem is that when we start to write about thermodynamics and we lose track of this classical mechanical work, that actually no longer holds. We actually now have path dependence. So the way we express this path dependence in thermodynamics is instead of writing dW, we put a bar through this D. And this signifies that this is not a perfect differential. So a perfect differential we could just write with the D, right? But this bar is signifying that the path that this dW takes matters, right? Plus d bar Q. This is the differential first law of thermodynamics. And it may seem pedantic to keep track of this, but conceptually it allows us to remember what we're doing when we make these thermodynamic assumptions. So now let's ask, what is dW? Let's try to quantify it. So what is dW? Well, we can make an argument for this term by considering something known as a material body. A material body is just a continuum agglomeration of matter. So you could just think of this as like a blob of matter, right? And of course, the way that we're drawing, it's hard to tell, but this in principle is a three-dimensional surface, right? And what we're going to do is we're going to consider a surface element, dA. So dA is like a differential sized surface element. So it has units of area, right? And what we're going to say is, let's consider that if we exert a force on this boundary across A, what is the work on that boundary? So if you have this surface element dA, right, and you exert some force on it, it's going to displace, it's going to move. So let's suppose it moves here, right? So if dA doesn't change, but the surface element pushes out, what's happening? This material body is deforming. It's either bulging out or sucking in, right? Now, if this results in some displacement, right? So what can we do? Well, we can say, in order for this to happen, we had to exert some force. We're going to call that force TdA. So this is the stress over this entire surface element, TdA, right? And then to displace it, we displace it by some amount, dl, right? So what's the work in this situation, or the change in work? Well, the change in work, and this is mechanical work, right? Because we're performing actually motion on a boundary, right? The mechanical work, if you recall, is just the force times the displacement, right? So, and we can rearrange that as well. So we're going to say this is the displacement dotted with the force, TdA, right? Now the question is, what is this T, right? Well, T is a stress tensor, which I'm not sure if all of you are familiar with, but all it is it describes the way that forces interact on this surface, right? You could have forces that push in on the surface, that slide along the surface in all possible directions. And the way this is usually expressed is as a matrix, right? So usually we have something called the stress tensor, which I'll denote as capital T. And it's a matrix of stresses. And these stresses are along all three directions, x, y, and z, in those directions. So you end up with a 3x3 matrix to describe all of this, and I won't write out all the terms. And some of you are probably already familiar with the stress tensor. But in this case, what causes this deformation out is just the pressure, it's just the stress that's normal to the surface. So if we have a surface and we draw an outward unit normal, right, that's what's going to perturb the surface out, right? So if we look at T dot n, so essentially what is the stress that's normal to the surface? We're going to say that this stress that's normal to the surface is the pressure, and by convention we do minus. It's the pressure, so the force pushing inward, in that direction normal to the surface. Now, of course, we've made an assumption here. We've made an assumption that these diagonal terms here are 0. So this can hold in a few cases. You could have something where there is no viscous force, which is what these terms are called. So you could just assume them to be 0. You could also assume that this boundary moves so slowly so as to not cause any transfer of energy through these viscous interactions. And this equation will still hold. But it is subtle, and this argument is a little hand-wavy in that regard. So we're going to make that assumption. Assume no viscous force. Assume no viscous forces. And we get this, that T is equal to the minus P, the minus pressure, exerted on the boundary in the normal direction. Now, if we're going to write this out over our volume element, right, then we have that dW is equal to dl dot minus Pn dA, right? Well, if we want to look at this deformation and this force over the entire surface, what do we need to do? We need to integrate this over the entire surface A, right? So we'll take an integral over A. Well, what is this? This would just be the total work now, the total mechanical work. Integral over A. And what we can do is pull this pressure out because it's a constant. Minus P, integral over A of dl dot n dA. Now the question is, what is dl dot n? Well, dl dot n is essentially the amount that dl, like the length of dl in the n direction. Well, that is just equal to the height of this object, this cylinder that we've carved out. So then what is, so if this is the height, we'll call it dl, we can call it h. If this is the height, and this is the dA here, then the product of the two is the volume of this cylinder. So we have the volume of this cylinder integrated over the entire surface. Well, all this is the total volume, right? So what we can write this as is that the work is equal to minus P integral over the entire surface, right, of dV. Now, we have some weirdness here. We actually, when we do this transformation, we change our bounds, so it's truly an integral over the entire volume. Now, that looks like something you probably have seen before, right? If you were to look at only a single dA, then this expression for dW here would end up being that dW is equal to minus P dV. Now, you've probably learned this before in your other thermodynamics class, but this is where this is a physical argument for where this could come from. We've actually just gone from looking at a material body, deriving through what the work would be, and calculating this dW equals minus P dV. So we've just learned where P dV comes from, or the change in work comes from. But now we're going to talk about thermodynamics in sort of a new way, maybe a way you haven't seen before. And this is with respect to the thermodynamic postulates. So this approach is, I would say, was popularized in Herbert Callen's book, An Introduction to Thermodynamics and Thermostatistics, postulates. And this approach is more mathematical than maybe what you're used to. I always struggled with thermodynamics because it felt very hand-wavy and it didn't make sense where things came from. And while this approach introduces a set of postulates that will lead us to all the thermodynamics we need, what I found is that it feels a little bit more mathematically concise, and it's a little bit easier to get started with thermodynamics in this way. So the first thing I'm going to mention is that thermodynamics is concerned, thermo is concerned with both reversible and irreversible processes. And we're going to have to discuss what that means. Thermo is concerned with both reversible and irreversible processes. An irreversible process is a process in which you have some state A, you start to go to a state B, and you can't go backwards, right? Now there's restrictions that cause you from not being able to go back from B to A, and we're going to discuss those. And this would be an irreversible process if you can only go in this direction. A reversible process, on the other hand, you could go from A to B, right? And then you could go back, and you have no penalty. For now, we are going to discuss equilibrium systems. So what do we mean by equilibrium? For now, we are going to study equilibrium processes. We are going to study equilibrium processes. Now, a system at equilibrium, at some state of equilibrium, bounces around, it sort of fluctuates in its properties around that equilibrium point, right? And for now, our working definition of equilibrium, so we're going to say an equilibrium state. An equilibrium state is a state of a system such that, is a state of a system such that given a set of internal parameters, so these are parameters that describe the system, and we're going to be explicit about what these parameters are. They're going to be the internal energy, the volume, and the number of particles of each type. So we're going to say Ni, where I ranges from 1 to N, and I is a chemical species. So it could be, if you have a mixture of something like neon and argon, right? I would be, you'd have neon, argon, so you'd have 2 of these guys. And of course, you're going to have N, the total number of distinct chemical species in your system, right? So an equilibrium state is a state of the system such that given a set of internal parameters, the internal energy, the volume, and the number of particles of each type, that a system, a thermodynamic system, tends to evolve towards. So an equilibrium state for a given set of conditions is a state of a system that it tends to evolve towards, right? So what does that mean? It means that if given enough time, you put a bunch of particles in a box with specific internal energy, volume, and number of particles, then the system is going to evolve towards a state, and it's going to stay in that state, and we're going to define that as the equilibrium state. So our definition for an equilibrium state is going to lead us to our first postulate of thermodynamics. So postulate 1, there exists particular states of a system, called equilibrium states, that are completely characterized. So we are postulating this. We have no way to show or prove this, but we're going to postulate that they are completely characterized by the internal energy, the volume, and the number of particles of every species in the system. This is postulate 1. Now, it is possible, and this is worth noting, that if the systems get more complex, you may need more than this, right? So, For instance, if you have something like elastic strain, we may need to add elastic strain. So we're going to do a little star. We may need to add other variables for more complex systems. For more complex systems. We are not going to deal with these directly, but some examples could be things like elastic strain or electric dipole moments. Electric dipoles. So, electric dipole moment. So those may need to be added into this postulate depending on the complexity of the system. But for now, we're going to take this one as it is. The second postulate, postulate 2. Now that we've established that there are, or we've postulated that there are these equilibrium states fully characterized by internal energy, volume, and the number of particles, postulate 2 says that there exists a function, so there exists a function S. So a function S, such that S is a function of the internal energy, the volume, and the number of particles of all the species. So there is a function like this that exists, whose extensive parameters take values so that this function is maximized at equilibrium. So that this function is maximized. At equilibrium. So if we are in an equilibrium state, this function S is at a maximum, and when we say its extensive parameters, these are parameters that depend on the size of the system. That includes U, V, and N, right? If you double the size of your system, you double the number of particles. If you double the size of your system, you could double the volume, double the internal energy. These are extensive parameters. So what is important, and the big important note on this one, right? So we've postulated the existence of this function S that's maximized at equilibrium. This only applies to equilibrium states. Only applies to equilibrium states. In general, it will not apply to non-equilibrium states. Now, you might have guessed, this function we're going to give a special name. S is going to be called the entropy. So for now, we're just postulating the existence of a function. We're going to call it entropy. And we're going to say that this function is maximized at equilibrium. Postulate 3 is related to the properties of this entropy function. Postulate 3 says that entropy is additive over subsystems. Is additive over subsystems. Furthermore, S, the entropy, is continuous, differentiable, and monotonically increasing. With respect to energy. Now this leads to a bunch of corollaries, right? So we're assuming that entropy is additive. This means it's an extensive quantity. Furthermore, if S is continuous, differentiable, and a monotonically increasing function with respect to energy, then we actually have a lot of properties that are going to fall out of this. And I'm not going to derive all of them, but here I'll write down a few. So we have corollary 1. Corollary 1. The sum over all systems alpha of S of alpha, so adding up all the entropies, we say it's an additive over subsystems. This is equal to the total entropy. So if we add up all the entropies of all these different subsystems, we get the total entropy. Corollary 2 is that the entropy is what's known as a homogeneous first order function of the extensive parameters. What does that mean? First order function of extensive parameters. What that means is that if you take your entropy function and you change its arguments by some parameter lambda, so we multiply everything in the system by lambda. This could represent doubling the system size, for instance, if lambda was 2 or whatever, just changing the system size by some scalar. This is equal to lambda times the original entropy. So it's almost as if by doubling or changing or multiplying your system by a certain scalar, all you've done to change the entropy is multiplying the original entropy by that same scalar. The system is twice as big, you have twice as much entropy, right? Corollary 3. The fact that the entropy is monotonic implies that temperature is non-negative. So if S is monotonic, and we'll introduce this in a little bit, this definition, then temperature is strictly positive. Well, and we should say it's not strictly positive, it's non-negative, so it could be equal to 0 if S is monotonic. The reason for that is that T is defined as, or we should say 1 over T, we'll find to be defined as the partial derivative of the entropy with respect to the internal energy at constant volume and number of particles. If S is a monotonic increasing function, then a positive change in the internal energy must correlate to a positive change in the entropy, right? So what that means is that this is a positive quantity. If this side is a positive quantity, we can say it's greater than or equal to 0, right? Then that means that T is greater than or equal to 0. So that implies T is greater than or equal to 0. And we'll get into these definitions before, but this monotonic property is a corollary of this postulate. Or the temperature being positive is a corollary of this monotonic postulate. The final corollary from postulate 3, corollary 4, is that entropy can be inverted. S can be inverted with respect to energy. Inverted with respect to energy. The reason for this is that if S is a monotonically increasing function of energy, then there's always one S for one U, right? That means if you invert it, that the inverse is a function, right? And not only is there an inverse, but because we have the continuity and differentiability of S, U, right, or this inverse, is a differentiable and continuous function of S, V, and N. So if we can start, the idea behind this corollary is that we can start with S as a function of U, V, and N, and we can invert it to find U as a function of S, V of N, and U will be continuous and differentiable. And again, we're not going into the actual proofs of these things, but these are going to fall out of the postulates that we just proposed. The final thing we're going to talk about today is postulate 4. The final postulate of this lecture. And that is the entropy vanishes at t equals 0. The entropy vanishes at t equals 0. So S equals 0 when t equals 0. You may have heard of this as the third law of thermodynamics. So basically what we're going to find is that armed with these postulates, we're going to be able to do a lot of really cool thermodynamic stuff. But for now, I'm asking you to accept these as what we're going to do is say that they're true and then see what the consequences are. And what we're going to do is we're going to find that those consequences actually align with our descriptions of thermodynamics, our experiments, and our intuition, right? So this is the first lecture on this postulate approach. I hope you found it interesting. It's a very different approach than maybe what you're used to learning in your engineering thermodynamics class, where they introduce things like energy and entropy balances very quickly. But here what we're going to do is we're just simply talking about the existence of this function and its properties, and that's going to lead us to understanding really at a nice mathematical level the interplay between all of these thermodynamic variables. So thank you very much, and we'll see you next time.